Hey, physics babies. This is Pandemic Education, episode 9. We're going to get started talking about simple circuits. This is Unit 5, Lesson 5. Here we go. All right, so like I said, Unit 5, Electricity and Magnetism, and today we're talking about simple circuits. So our objective, this is a bit of a continuation from our last class. Last class, we learned how to actually draw these simple circuits and indicate the direction of conventional current flow. Today, we're going to be talking about how power, current, potential difference, and resistance are all mathematically related. So electricity flows like water, all right? There's a direction that it's going to move, and there are certain things that we can do to make it move quicker or slower, so to speak. So on this side, we've got a little, water pump, and then on this side, we've got an actual circuit, and throughout the lesson, hopefully we'll get to see how they're similar. So there are a few different pieces that we need to talk about when we're talking about circuits. The first one is current. We use a capital I to represent current, and our unit to measure current is amps with a capital A to represent it. And current is just the flow of charge through a circuit. The similarity is the flow of water through a pipe, right? It's got to keep moving. It's got to go somewhere. An ammeter measures current, right? And ammeter, amps, current. Hopefully we can kind of keep all those pieces together for us. So I want you to look at this first problem and tell me, if we put an ammeter right here, would we get a reading on it? Think about it and tell me yes or no. Hopefully you said yes, the current is clearly flowing through the circuit. I see that the switch is closed, the light bulb is on, which means current is moving. For an ammeter to get a reading, the current has to be moving through it. What about over here if we move to this picture on the right, though? Would we get a reading if we put an ammeter right here at the same spot? Take a sec, think about it. Hopefully you said no. In this case, the switch is open, which means that the current is no longer flowing, which means my ammeter would not be able to measure anything because there'd be nothing going through it. Closed. Yes, circuit's closed, so there's current flowing. This is open. No, there's no current. Our ammeter would read at 0. All right, next up, resistance. We use a capital R, to talk about resistance. And the unit that we use is called ohms. And the symbol for it looks like a funny little upside down horseshoe. And it's got these 2 little feet sticking out of the sides. Practice, I'm sure you'll be able to get really good at drawing ohms out. So resistance is just a material's ability to resist or restrict the flow of electricity. So an example, if we're talking about water flowing, if we've got a really large pipe, a lot of water is able to go through it. But what if attached to that large pipe, we make a really small pipe fit? Well, not as much water is going to be able to get through there as quickly. We are restricting the flow of water. A resistor acts very similarly. It restricts the flow of electricity from one side of the wire to the other. All right, next up, voltage, capital V. Please note that this is capital V, not delta V. There is a difference, all right? Our voltage is the electrical pressure that causes charges to move, and it's created by a difference and separation of charge. So it's created by an electric potential difference, delta V. But the actual thing that we are measuring, voltage, is just V. Unsurprisingly, we use a voltmeter to measure voltage, right? It's crazy. Voltmeter, voltage, volts. It's like every once in a while scientists think and make things kind of make sense. Looking at these 2 pictures, so on the left, the water won't flow if the 2 ends of the pipe are at the same potential. So they're at the same level. The water's not going anywhere. In this case, we wouldn't have a voltage reading if this was like an electrical wire. If we move to this picture on the right, the ends are at 2 different levels, so the water would flow from one end down to the other. It would have a separation. There'd be a difference there, and then we would actually get a measure on a voltmeter for a reading. it's a little weird, I promise. As we kind of get some more examples down, it'll make more sense. If you're having any questions on any of this, please make sure that you write them down and come to office hours to ask me. I'd love to hear from you. I miss you all a lot. All right, moving on though. So now getting into our mathematic relationships. Please make sure you write all these down, pause the video if you need to, label it, make sure you got all this down. So V equals IR. This means that our voltage will equal the current times the resistance within a circuit. Voltage is measured in volts, current in amps, and resistance in ohms. All right, another formula, our electrical power, capital P for power, and remember, power is measured in watts. Think about a light bulb. The power of that light bulb is measured in watts. Power is equal to the voltage times the current. It's actually how we determine the watts on a light bulb. It's equal to the voltage times the current that go through that light bulb. Again, write all this down. Make sure you've got it on a nice formula sheet that hopefully you've been creating and keeping up with. All right. I would also highly encourage you to copy down this table. This kind of is a nice little overview of all of the pieces that we need. If you've already written down all of these vocabulary words with their symbol, their units in words, and their units in symbols, then I guess you don't really need to. If you haven't, I would do it right now. And then maybe add another column to do like a quick definition of what these things are. Pause me if you need to get all this down, but when you're ready, I will keep moving. All right, so I've got 3 example problems for us to do today, and I tried to set it up so that you don't have to see my chicken scratch, so we'll see how it goes. Our first example, we've got a 12-volt battery that causes a 3-amp current through a light bulb. So 12-volt battery, we've got 3 amps of current. I want to know, first, what's the resistance in the light bulb? And second, how much power is it drawing? So thinking about our problem A first, we know that I equals 3 amps. We've got that current right here. We also know, that our V, voltage, is 12 volts. So we want to know our resistance. What formula would we use that's got these 3 variables inside of it? The one that comes to my mind is V equals IR. Oops, I typed it wrong, I'm sorry. V equals I times R, not divided by R. Times R, let me see if I can fix that. Times R. All right, so next we need to, guys, I'm so angry at myself. I just messed up all of my hard work. Times R. Times R. So what are we going to do to get R all by itself? If we're multiplying, we have to do the opposite of multiplication, which is division. So we're going to divide both sides by 3. What is 12 divided by 3? 4, miss. So we get that our resistance is equal to 4. And what's our unit? Ohms. And it looks like a weird little upside down horseshoe with the 2 feet. Easy peasy. And then you can either include the symbol or write it out. As you're getting used to it, I would actually love to recommend that you try doing both, because this one's a little not intuitive, right? We go from ohms to this weird Greek letter that we've never seen before. So I would maybe kind of include both in your final answer. Look at that. All right, next question. We need to know how much power it's drawing. So again, our givens, we've got 12 volts equals V, we've got I equals 3 amps. We are looking for our power. What formula are we going to use? Power equals V times I. Our power equals the volts times the current. Filling in what we know, we've got that our power is equal to 12 times 3. What's 12 times 3? 36. And make sure you include a unit at the end. Our power is equal to 36 watts. Please make sure you write down these examples. Don't make the same mistake I did with division. It's multiplication. Sorry about that. And then when you're ready, we're going to move on and do another example. Right. So let's clear off my e-notations. All right. So next problem, a light bulb in a circuit with a 12-volt battery uses 24 watts. We want to know what the resistance is of the light bulb. So working through this, our givens, it's always going to be the first thing that you list. If you're not listing your givens first, you're doing it wrong. All right, our V is equal to 12 volts. Our power is equal to 24 watts. And again, this is why that table is going to help you. Notice that these problems aren't saying it's got a power of 24 watts. You need to see this and know that it's talking about power. Use that table. I'm literally not going to see you until the end of the year. I don't know what resources you're using. Take advantage of it, okay, guys? I'm not asking you to memorize it. Make good use of your resources. Anyways. Oh, that's not what I wanted. Sorry, I need to go through and show all this work. So, don't mind my lovely chicken scratch. So we've got volts, we've got power, and we want to eventually get to our resistance, R. So what formula did we learn that's got R in it? We've only learned 2. So the one with R, we've got V equals I times R. Well, this is a really great formula. The only problem is we don't know what I is. We know what V is, we want R, but we're missing I. Do we have a way to get our current I? Well, we just learned that power is equal to V times I. So if I use this formula, we'll find I that we can then plug into this formula to solve for R. This is one of those problems, it's a couple of steps, but they're pretty easy. So we'll do this one first and then this one second to get to our final answer. So power equals V times I. We've got, I'm going to show the math over here, 24 equals 12 times I. Plugging in our values that we know. What are we going to do to get I all by itself? Inverse operations, we'll do division. Let's divide both sides by 12, because whatever we do to one side, we have to do to the other. Those go away, and we get I equals 24 divided by 12 is 2. I'm going to include my units because, you know, that's the right thing to do. We measure current in amps, capital A. All right, now that we know my amps, we know my I, we can take this and plug it in right here. So V equals IR. We'll say 12 equals 2 times R. What are we going to do to get R all by itself? Inverse operations, we'll do some division. Let's divide both sides, because whatever we do on one side, we got to do the other. We got to move this 2 over. Boom. 12 divided by 2 is 6. We're talking about our resistance. What is the unit on resistance? Ohms. Boom. There we go. Couple extra things that we need to do, but still not necessarily a particularly challenging problem. All we're doing is multiplication, guys. Multiplication and division. Real straightforward. All right, make sure you copy this problem down, and when you're ready, I'm going to keep going. All right, this is our last example. In a circuit, what happens to the current if the voltage is tripled and the resistance remains the same? So we've got a voltage that's being tripled, which means multiplied by 3, in case you forgot what tripled meant. But our resistance is going to be constant. We want to know what's going on with our current, I. What equation are we going to use to figure out what's going on with I? Well, hopefully the one that came to your mind is V equals I times R. So we've got this equation, but now I'm telling you that instead of it being a V, we've got 3V, which is equal to I times R. R is the same, and we're adding this 3 to in front of my V. What does my current have to do so that both sides stay equal? Hopefully you were able to realize that our current also has to be multiplied by 3. The current in the circuit needs to be tripled, okay? Our new current will be 3 times as big as the old current, and we could just say it's equal to 3I. Well, that's all I had for you. Hopefully you were able to follow along with those examples. Hopefully you wrote them all down in your notebook. As for the kind of exit ticket and assessment for today, there are 4 guided practice problems that I want you to do and submit your answers to. I'll post them on Google Classroom. You'll see the document. It's got all the problems that I just did. It's got guided practice, which will be your assessment. And then it also has independent practice. Do the independent practice before you submit your assessment. And that'll be it. I hope you guys are all doing well. I love you tons, and I miss you like crazy. Stay safe, wash your hands, and I hope to see you soon. Love you lots. Bye.